I mentioned it before that all organic acids are weak acids. They represent an important group of those weak acids. They belong to a functional group within organic chemistry. All of them have a special signature, which is the carboxylic function, and that's why they're also called carboxylic acids. And that carboxylic is just this portion here, the COH function. They are attached to a radical R group, which is just another carbon chain. So this is the carboxylic functional group for the weak acids. So they make, when they dissolve in water, they ionize, forming the H3O plus the conjugate base, which is the carboxylate ion, COO minus. And this is the conjugate base. So this is the molecular structure of that base, the carboxylate base, and can be represented as two resonant structures, where this pair of electrons here are delocalized. Yeah, and here. So there's not a unique structure for that group, the COOH. So it could be COOH minus. So it could be here or here. In other words, the resonant structure shows that the localization of these pi electrons there. So we have oxygen and oxygen there. And the pair of electrons can be either here or there. So that dots represents the localization of that charge, making it a very stable structure. So this structure here, the conjugate base, is stable, making this bond oxygen, hydrogen, a weak bond, giving the possibility for the protonation of water. So it's pretty stable. And that's a property of all carboxylic acids, all organic acids. Here is the structure for acetic acid. And look the structure here for chloroacetic acid. What is the difference between these two? Look, this hydrogen here has been replaced by a chlorine, an electronegative element is more electronegative. So, and look, the Ka for this acid compared with this, the one that has the chlorine in the structure. This is weaker because this pair of electrons here can delocalize once they form the conjugate base. However, here we have a stronger acid. So this one makes the chlorine makes this bond stronger. Now, I showed you before, what happened with the salts. Not all salts are neutral. Salts can be basic, acidic, or neutral. And that is going to depends on the nature of the cation or anion of the salt, depending on what species is forming the salt. Let's just remember where salts comes from. All salts comes from the reaction. Well, the main source of salts comes from the reaction between acids and bases. So when an acid reacts with a base to form a salt plus water. And this is called a neutralization reaction. Neutralization reaction. Salt is being produced here. So let's represent generic acid. So the acid HA reacts with a base to form the salt and the water. So usually we're working with hydroxides, so it's going to be a hydroxide. So it's going to form the salt, Ba, plus water, H2O. The net ionic equation will be H plus from here, from the acid, plus OH minus from here, from the base, to form water. And this is what we call the net ionic equation for a neutralization. That's an important question. That is an important question there. And here we have an equilibrium. So again, this is the net ionic equation for a neutralization reaction, the acid-base neutralization, reaction of acid and base. And that's true for any strong or weak acid and base. So you can have a combination here of acids and bases. You can have a combination of a strong acid and weak base. You can have a strong acid, strong base. You can have a weak acid, a strong base, or you can have a weak acid and weak base. Any combination of strength of acids and bases, you will get always a salt, and this is the salt, and water. Notice the composition of the salt here. The cation, which is the B in that structure, comes from the base, and the anion comes from the acid. So let me write that here again. The salt is made of two parts. Anion, that's the negative portion, negative ion in the structure, and this is the cation. This is the positive part of the structure. Cations from the salt comes from the base. The anion of the salt comes from the acid. So remember, salts comes from the reaction of acids and bases. And so you have to analyze what acids and bases are making a salt. For example, sodium chloride. We have the cation and we have the anion. Where this cation Na plus is coming from? It's coming from a base, NaOH. Where it is coming from? Usually from the acid HCl. So those two will react together to form the salt plus water. Everything in aqueous solution. And this is pure liquid. Here, this is aqueous. This is aqueous. And this is pure liquid. So once you realize that, you can identify the strength of the acid and base that is making the salt. Sodium hydroxide is a strong base. The strong base makes a weak conjugate acid. So you will have the conjugate acid here on this portion of the structure. And the Cl minus is the conjugate base of the strong acid. Last time we said that strong acids make very weak conjugate bases, too weak to react with water. So no secondary reaction of this ion Cl minus aqueous with water. Remember, once this is formed in aqueous solution. That means the salt will exist only as ionic species in the solution, plus Cl minus. So once the base and the acid forms the sodium chloride, it will remain as ions. And there's a water there. Water is the solvent, so they are colliding with water molecules all the time. But this is too weak to react with water. So no secondary reaction comes out of here. There's no hydrolysis of that ion. What about this? This, the cation of that salt, comes from a strong base, making it a weak conjugate acid, too weak to react with water. So again, no secondary reaction of sodium plus with water. As a result, we have a neutral salt. So this salt will not change the pH of the solution. So that's the analysis we need to make every time we have a salt. What is the nature of the salt? What acid, what is the strength of the acid making or giving the anion in the salt? What is the strength of the base producing that cation, that conjugated acid? So let's do some examples. Let's check this one. Sodium fluoride. It's a salt. The question is, what is the nature of this salt? When we dissolve this salt in water, what kind of solution is it going to make? Acidic solution, neutral, or basic solution? And we need to do the analysis. We need to think, where is this salt coming from? So what do you think? What base and what acid is are making this salt? Sodium, the first part, from hydroxide, right? So what hydroxide can possibly react here to give off Na? Sodium hydroxide, that makes sense. So sodium hydroxide, so this is basically the way we need to go backward a little bit to figure how that salt was made, what base was used to make that salt. So chances are that this sodium comes from sodium hydroxide. Plus the fluoride portion of the salt. Yes, HF on an acid. When these two, the acid and base react, they form the salt and water, liquid. Now let's do the analysis. This is a strong base, therefore making a weak conjugated acid here. What about this one? This is, remember we have this on the list of weak acids. So this is a weak acid, producing a strong conjugate base. All right, so let's do the analysis. This is weak. Na plus is a weak conjugate acid, too weak to react with water because it comes from a strong base. Fluoride, F minus, comes from a weak acid. Therefore, F minus is a strong conjugate base. Strong enough to react with water, with the water that is present in the solution. This is aqueous. So it's going to be a secondary reaction. So F minus, wherever the source, is going to be a weak acid. So F minus is a very strong conjugate base. So you can have F minus in any form. You can have this salt, KF. You can have NH4F, any source, right? You can have lithium fluoride, any salt containing this ion will produce, once you dissolve that salt in water, it will produce the ion. And we know that ion is strong enough to react with water. And the result of that reaction, which is called the hydrolysis or salt hydrolysis, will form the weak acid and will produce the hydroxide ion, which is a strong base. And you know, once you see the OH minus in solution, you say this is basic. The solution is going to be basic. So look, you have water. And you add any salt containing F minus. Let's say NaF. This initially, the pH of this is, since we have pure water, the pH is 7, it's neutral. The question is this pH going to change when we add NaF to that solution to make NaF solution there? The question is yes. So how is the pH going to change? Is the pH going to increase or decrease? The answer is the pH is going to increase once we add NaF. Not because Na. We know Na comes from a strong base. Therefore, this is too weak to react with water. So we don't have to worry about this. This is like a spectator ion. That's why you don't see it here. And we don't even need to represent it there because nothing is happening. There's no hydrolysis. There's no reaction between Na plus and water. However, the F minus there, this ion, is going to produce, through that hydrolysis, through this reaction, is going to produce also OH minus, making the solution basic, bring the pH about 7. So the solution, we say we have a basic solution because of the OH minus. And the OH minus came from hydrolysis of the salt, F minus. So that's the analysis we need to make. And we can actually measure the pH for that solution. Let's do one more. For the case of weak bases, we have this example. This is a conjugate base. If this conjugate base comes from a weak acid, therefore it's going to be a strong conjugate base. It's strong enough to react with water. As a result of that reaction, which is hydrolysis reaction of that anion, will form a weak acid the same acid that forms initially the salt plus OH. So this is the strong base producing the basic solution. Examples of salts that can make basic solutions: because of the hydrolysis are the acetate ion, the nitrite ion, and the hydrogen carbonate ion. So these ions, any salt containing these ions will make basic solutions. When you add that into water, you know the pH is going to be about 7. So we have basic solutions. And notice, this basis comes from weak acids. Weak acid made this strong conjugate bases. What acid made this? Acetic acid. What acid made this ion, NO2? Nitrous acid. What acid made this base? HCO3, hydrogen carbonate or bicarbonate. Yes, the carbonic acid. Interesting, right? Because the weak acids are making these bases, but these bases, conjugate bases, these salts can react with water, increasing the pH. Examples of salts, common, usually you have salts of sodium. Remember, all sodium salts, all first group salts of metals of first group of the periodic table, like sodium, potassium, lithium, rubidium. They are soluble in water. So it's easy to find these salts. Here, lithium, for example. Calcium acetate, second group. Barium nitrite. So we don't worry about these ions because we know those comes from strong bases, so they are too weak to react with water. We should be able to recognize the ions in the salt that can hydrolyze to change the pH of the solution. So let's do this. The calculation is pretty simple because we use the same concepts we've been using on equilibrium. Calculate the pH of 0.10 molar solution of sodium fluoride. NAF at 25 degrees Celsius. We set the equation. The problem gives you only this information. And I always have the question, how do we start? How do we know what reaction we need to write? Well, the hint, the best practice probably will be to go backward. Write down your salt, wherever the salt is given in the problem, and dissolve that salt in water first, so you will see it. So let's dissolve this in water. Let's put on the water. And what's going to happen once you put the salt in water? Is it going to ionize or is it going to dissociate? What is the proper word to describe the process? Let's analyze the first one. Is it going to ionize? No. It's not going to be ionized because they're already ions. It's a salt. Remember, the salt is made of a cation and an anion. There they have the charge already, Na plus, F minus. So they are not going to ionize because they are already ions. So what are they going to do? They are going to dissociate. Water is going to help that dissociation, forming Na plus aqueous plus F minus aqueous. So this is not a reaction, it's just dissociation process. You are dissolving the salt into water. That's what happens when you add a few grams of sodium, the salt, NaF, into water. The water will help to break down the crystals into its ions. It's a dissociation. Now you can see it better. And now you remember Na plus? No, don't worry about that. There's no reaction with water. No. There's not going to be hydrolysis on this side. This comes from a weak acid, therefore it's going to be strong. Yes, it's going to be a reaction with water, a hydrolysis, and that's the one that is going to change the pH. That's why the question is, calculate the pH of solution of sodium fluoride. So you should be able to identify what ions comes from your salt and what ion is going to change the pH. If one of the ions is strong enough to react with water, it's going to make a change in the pH. If both ions are too weak to react with water, therefore no change in the pH of the solution, so that we're talking about a neutral salt. So once you identify your strong conjugate base, then you can write your hydrolysis equation. So this is going to be the hydrolysis equation. This is just dissociation of your salt, or you are dissolving the salt. So the hydrolysis is the reaction of your conjugate base, your salt, your anion with water. So this is strong. It's going to accept proton from here. Remember, you can write the water as HOH, so you can see it better. This is a base. Negative charge is going to take the hydrogen, forming HF, and what is left? OH minus. Look, this charge here comes here. And you know right away that the solution is going to be basic because that ion is producing hydroxides, the most basic species. Now this reaction, since this is a base reaction, has a Kb. And that's the reaction we need because this equilibrium law includes the OH. So if we have the OH minus, we can find the P from here, POH. Once you have the POH, you can find the pH. So that's the strategy. However, we always, when we're doing this hydrolysis, we find a little situation. This is the Kb of a conjugate base. Do you remember how to find that? How do we find Kb's of conjugate bases? Simple. Use the relationship I showed you last time to find the Kas and Kb's of conjugate acids and bases. And that's easy because we know Kw, which is 1.0 times 10 to the negative 14, and the Ka is the constant of the weak acid making the ion. What is the weak acid making the ion? What weak acid was used by the manufacturer to produce the salt? Probably HF. So we can assume it's HF. And we know this is a weak acid and the weak acids have Kas, and we can find this on the list. If you go back to the previous video, I showed you the list of Kas of weak acids. So you can find them in the back of your textbook. Or a different source, you will find the Ka of HF is 7.1 times 10 to the negative 4. So using this relationship here, we find the value of Kb, the Kb of the conjugate base. Remember, you won't find a list of Kb's for conjugate bases. You won't find a list of Kas of conjugate acids. So we use this formula to figure it out. All right, so we have everything. We just found the Kb, and we just need to find this concentration. So we write the ice table. We have the initial concentration, which is given, initial concentration of F minus, initially 0, 0. The change is minus X plus X plus X. The equilibrium concentration will be 0.10 minus X, forming X and X. We plug that into the equilibrium law. Here we do the approximation to avoid the quadratic equation, and we find that X, which is the concentration of OH minus, here from the previous one. X is the concentration of OH minus. That's what we're looking for. We are not interested in this. No. What species changing the pH? Only this. That came from the hydrolysis of F minus. So this is the value that we're looking for, X. Happens to be the same as HF, but we don't care about this. We are interested in this. So we've just found that X, which is 1.2 times 10 to the negative 6 molar. We find the POH, which is 5.95. we use the second equation we learned before to find the pH. So 14 minus POH equals 8.05. So the pH of that solution, 0.10 molar solution of NaF at 25 degrees Celsius is 8.05. This is the complete, clear answer for the question. When you are solving problems, give the answer. Show the answer to the problem. Usually, or sometimes, students just leave it that way. So there's no answer. And I start asking, what is this? What was the point of doing all this? Right? There's no answer. So this is the way, the proper way to give answer to a problem. Now I can go here, it's very clear. I understand what's going on here, but the person who wrote this probably had no idea because they didn't give an answer. So make sure every time you solve a problem, give the proper answer. Here is the pH. Look, we were expecting, as we predicted, the pH to go up, right? So we said before that the pH is going to go up. It's going to be basic. And here is the demonstration. All right, let's see this case. This is another salt. And the previous salt, we have a conjugate, strong conjugate base, F minus. It could be any, you can do this procedure, this analysis with any salt containing a strong conjugate base. It's exactly the same procedure. The only thing is going to change probably is the initial concentration and definitely the value of the Kb for that conjugate base. And this exercise, we have a different salt, ammonium chloride. So what is your analysis? First, you dissolve the salt in water. And how do you call the process? You say dissolving, it's okay. What else? How do you call this process? The salt is breaking down into its ions. It's not making ions because they are already there. Ions are already there. This is an NH4 plus and this is Cl minus. It's a salt. So we cannot call this ionization because it's not making new ions. They were already there. So how do you call this? It's called dissociation. This salt is dissociating into ions, into its ions. It's breaking down into its ion in the aqueous form. Remember, in order to be ion, they must be in aqueous with water. All right, so once you do the dissolving process, you identify the ions. That's here is important in every problem. You do this, take the salt, dissolve in water to see the ions and then do the analysis. How do you start from here? Cl minus. What is this? A strong base? And you say, no, it's not a strong base. Why not? Because it comes from a strong acid, HCl. HCl is strong, making a weak conjugate base too weak to react with water. So this one will not react with water. So we don't have to worry about this. This is just a companion here in the salt. What about this? Who's making this conjugate acid? Yes, NH3, right? NH3 reacts with water to form NH4 plus ion. So probably the manufacturer used this reaction NH3 plus HCl to form the salt. Then they take out the water. Remember, this is aqueous. Take out the water, crystallize, get the crystals, and sell it as ammonium chloride. Very important, because you can add this to the soil also to change the pH of the soil in a very gently manner, and also adds a lot of nitrogen to the soil. So that salt you buy is a solid, and that's why you have a solid. You dissolve into water and get the ions. But since this ion comes from the weak base, that will make a strong conjugate acid. And you say strong enough to react with water. So that goes to the hydrolysis. Here we have hydrolysis. Reaction. The ion from here will react with the water that is present there. And what is the result of that? It forms, this is an acid, it's going to donate that proton to water. Remember, you can write water as that way so you can see it better. So this has a pair of non-bonding electrons there. It's going to take that hydrogen, forming H3O plus and an H3. And this is the part we're looking for. Look, that salt this is water, this is the pH. It's pure water, right? So the pH is 7. It's neutral. Before we add the salt. Add the salt, what's going to happen with the pH? Will go up or down? You don't see, and this is tricky because when you add the salt, you don't see H plus, you don't see OH minus here. So you say, probably it's neutral. Well, it's not, because the analysis shows that the reaction of this portion of the salt with water will actually form H3O plus, causing the pH to go down. So that's going to form a acidic solution. That's why we say this is acidic salt, because of this. And that will happen with any strong conjugate acid. And the mathematical treatment to solve problems is similar to the one we did before. Let's do this one. Calculate the pH of 0.10 molar solution of ammonium chloride at 25 degrees Celsius. So again, the strategy, what is that? Take your salt and dissolve in water. NH4, Cl minus, is solid. It's a salt. So it comes in crystals. Pretty similar to table salt. That's why you don't taste chemicals, because a lot of chemicals, they look similar. So you cannot, you see white, nice crystals, you cannot assume this is sodium chloride. Somebody says this is a salt, and you cannot assume that's table salt, sodium chloride, no, because there's so many salts. Some of them are really toxic, poisonous, can kill you in a few seconds. So don't taste chemicals. Don't go by the appearance. You need to read the labels, and you need to label any chemical. You put a chemical on a bottle, label it to prevent accidents. So everybody will know what is inside of the bottle. You take the solid, dissolving water to separate the ions. So it's a dissociation, NH4+, aqueous. So you have water, right? Here. Plus Cl minus. And do the analysis. This conjugate base comes from a strong acid, therefore too weak to react with water. No reaction here. No reaction with water. So don't worry about that. What about this? Ammonium ion comes from a weak base, NH3, therefore makes a strong conjugate acid, strong enough to react with water, and that's the one we are going to do hydrolysis. So that means the ions, once it gets in contact with water, will react with some of the water to form an H3 and H3O+. So here we have a balanced equation for that reaction of ammonium and water. And this is the Ka. This is an acid. It's going to work as an acid because it's a strong acid, strong conjugate acid. So the Ka equals the equilibrium expression for that equation. However, same situation. This is the Ka of this strong conjugate acid, and there's no list of Kas of conjugate acids. We need to find it, but that's easy. We just learned that we use this. This is especially made for the situation and only for the situation. So we need to find this. This is for the conjugate, and this is the Kb of the weak base that made the acid. And we know that already. This came from where? What was the base making this? Yes, NH3. NH3. So this one has a Kb. And we all know the Kb of ammonia, right? It's 1.8 times 10 to the negative 5. So Kw over Kb gives the Ka of that conjugate acid. We do the ice table, exactly the same situation. We do the ice table, initial, the change, the equilibrium concentrations, we plug into here because we want to know this portion to find the pH. And that happens to be X here. X will show the concentration of H3O+. We know this, we just found it. And we solve. We plug this equilibrium concentrations into this expression and find X. Like that. Also, we do the approximation to avoid the quadratic equation, find X, which is 7.5 times 10 to the negative 6 molar. That is the concentration of H3O+, therefore we can plug that number directly into the pH definition to find the pH equals 5.2. And don't leave it there. Don't leave it there. You need to write the answer. So the pH of a 0.10 molar solution of ammonium chloride at 25 degrees Celsius is 5.12. Your answer must match the question. I know during the test, you don't have time. At least during the test, what you can do is circle your final answer. All right. Metal cations that have a charge, they are cations, they can hydrolyze too. And also form complexes. At the beginning of the semester, we do some demonstrations, formation of complex, and we compare different salts. We use zinc, magnesium, copper, and some of them were able to form complexes and others were not able to do that. They do ionization too, also, changing the pH of the solutions. So for example, this one, this is aluminum. This is a complex of aluminum that goes through hydrolysis, producing H3O+. That means it can make this solution acidic. All right, so this is a summary of what I said already, the neutral salts, acidic salts. Some examples are here. So if you go through this table, we'll summarize, we'll show what we just said and we just did, including the samples. I prefer to do the critical thinking every time we have a salt instead of memorizing. Some people prefer to memorize this to identify the ions, the cations or the anions. Here we have a strong conjugate bases. These are weak conjugated acids, too weak to react with water. Those are strong conjugate acids that react with water, they change the pH. So just do the critical thinking every time you have a salt. Here are more examples, you can practice with those. It's exactly the same way we did it before. So I give you this for you to practice. And here the solution, don't cheat. Here is the summary of what we just said. When we have a salt, to make prediction if the salt is going to make basic solution acidic or neutral. When Kb of the base is bigger than Ka of the acid, the solution is basic. When Kb of the base is less than Ka of the acid, the solution is acidic. That means Ka is bigger than Kb. When the two dissociation constants are about the same, that means the solution will be neutral or close to neutral. So as I mentioned before, we did an experiment showing how some oxides of metals and non-metals react with water to form amphoteric hydroxides, basic solutions, or complex formation of complexes. Metal oxides react with water to form hydroxides, and usually those are very strong hydroxides. On the other side, on this corner, we have non-metal oxide that react with water to form acids. So this table can help you to make predictions or how to make acids or bases. So when you see a metal oxide, they will react with water, will form hydroxide. When you see a non-metal oxide, they react, they have the tendency to react with water to form the acids. These elements here that are in the border of metals and non-metals, some of them are semi-metals here. They have the tendency to have both properties, acidic or basic. So that makes them amphoteric oxides. Here are some examples of these reactions with water to form the hydroxides and to form the acids, the most common acids that we use in the lab. Some of them are amphoteric, for example, aluminum oxide. If aluminum oxide is placed with hydrochloric acid, there's a reaction forming aluminum chloride. So that means the aluminum oxide is reacting as what? If this is reacting with an acid, we recognize this is an acid. We are not sure about that. However, when this reacts with this and there's a reaction, this actual reaction, that means this is working as a base against the acid. But also, on a different reaction, aluminum oxide also is placed with a strong solution of a strong base, sodium hydroxide. And there's also reaction. We recognize this is a base, a strong base, and this aluminum oxide is reacting with the base. That means here, the aluminum oxide is an acid. Remember, acids react with bases. The result of this second reaction is this sodium aluminum hydroxide. This actual reaction. That means this aluminum oxide is amphoteric because it can work as a base or acid depending on the environment. For some metals, some transition metal oxides react with water to form acidic oxides, like this one, permanganic acid. Those are special cases. Just want to show a few of those here, like this chromic acid also, you see. So those are transition metal oxides reacting with water to form acids. These hydroxides here are basic. Did you see the hydroxide here? But they can be amphoteric also. They can react with acid or base. Here, the reaction of acid to make the beryllium 2 plus, and here the reaction with a base to form the hydroxide. So those are special cases, situations with some metals and non-metal oxides. Here is another example of the aluminum being amphoteric, reacting with acid or reacting with base. So yes, it shows the amphoteric property of aluminum compounds. The last topic is to give a few examples of Lewis acid and bases definition. Remember, there are two important definitions we use in chemistry regarding acids and bases, or acid-base theories. The Bronsted-Lowry, the one we have been using all this time, definition of acids and bases, and the Lewis acids and bases. I mentioned it last time. Let's remember that. According to Lewis, acid is a species that accepts a pair of electrons. Some species, some substances are thirsty for pair of electrons. They want to have more electrons in order to achieve a level of stabilization. And bases donate a pair of electrons. So it's another definition, another way to see acids and bases. And this definition covers mostly all of the Bronsted-Lowry acids and expands the frontier of acids and bases to substances that behave as acids and bases, but they not quite fall into the Bronsted-Lowry acid definition or basis definitions. Let me give you a couple of examples of that. Here, if I ask you to identify this species as Lewis acids or bases, notice that H plus wants to have electrons, right, to get stabilization. So this is going to be a Lewis acid. OH minus that has three lone pairs of electrons around oxygen wants to have or wants to donate these electrons in order to be stabilized. And the stabilization comes in the form of water. So we have the Lewis acid and the Lewis base. They fall pretty well. These two species falls pretty well into the definition of Lewis acids and bases. H plus can accept a pair of electrons from here, and OH minus can donate a pair of electrons to here. But also, we already recognize this as an acid according to Bronsted-Lowry. Right? And this species is a Bronsted-Lowry base too. So the two definitions agree in that part. Now let's see the second example. H plus plus ammonia. Which one is the acid? Which one is the Lewis acid? Which one is the Lewis base? Which one is going to donate? Probably it's easier for you to see who's going to donate the electrons. Look, nitrogen has a pair of non-bonding electrons. So that means this is going to make a good, a good Lewis. I was thinking about weak base. Lewis base, because has available a pair of electrons to donate. That's the definition of Lewis base. Lewis base is a substance that can donate a pair of electrons. To whom? In this case, to hydrogen. So hydrogen is going to accept a pair of electrons, that making it, again, as we see before, a very good Lewis acid. So that the Lewis definition of acids and bases for this particular example also agrees with the Bronsted-Lowry definition of acids and bases. For Bronsted-Lowry, acid is the one that donates a proton, and base, according to Bronsted-Lowry, is the one that accepts a proton. In some cases, it's not that obvious, like this case. Look, boron trifluoride, and ammonia. This is a stable structure. Do you notice something weird here in this structure? Do you? What is that? Octet rule. How many electrons around boron in this structure? 2, 4, 6. It's quite stable, exists, but it can be better, right? It can get more stable if achieves 8 electrons around boron. So that means boron lacks a pair of electrons. And how is going to get a better stabilization? So let's see what's happening when we do the electron distribution. The atomic number for boron is 5. So the electron distribution for boron is 1s2, 2 plus 2, 2p1. For the outermost energy level, we have two S and 2p. Two electrons here, there's 2s2 and 1 electron here. According with this ground state energy distribution for boron, boron will be able to make only one bond, but there's hybridization of orbitals here. If you can recall from your Chem 11 course. So this is the ground state, and this is the excited state. One electron from here, there's a transition there. 1, 2, and 3. Now that explains why boron is satisfied with only 3 bonds with fluorine. Every fluorine comes here and apports 1 electron here. So we have 3 bonds there. However, it can get better stabilization, having 8 electrons around boron. How? There's a reaction with this base, and that can be explained through Lewis' definition of acids and bases. This is reacting as a base because it has a pair of electrons that can donate, making it a base, and this can accept this pair of electrons, making it a Lewis acid. So we call this a Lewis acid, and we call this a Lewis base. So when you do acid-base reaction, it's important that you recognize what definition you are using. And it has to be acid-base, Lewis acid, Lewis base, or Bronsted-Lowry acid and Bronsted-Lowry base, but no a combination. Notice we cannot explain, if we try to use the Bronsted-Lowry definition of acids, how would you classify this? None, right? Because Bronsted-Lowry says the acid is a species that can donate a proton, but there's no proton here to donate. So Bronsted-Lowry cannot explain the acidic behavior of this species. However, Lewis' definition does. Now we understand that boron can accept a pair of electrons, making it a good Lewis acid. And this is the product, very stable structure. Look, count the electrons around boron, 2, 4, 6, 8. Around nitrogen, 2, 4, 6, 8. So that's the product. This concept of Lewis acid is widely applied in organic reactions. This is another example of Lewis acids and bases. Look, water. According with this, let's classify which one is the Lewis acid and which one is the Lewis base. Let's identify that. This mechanism is showing that this pair of electrons is going to be donated to the carbon. Therefore, here, water is working as a Lewis base, right? Because Lewis base donates pair of electrons. Since this carbon is the one that is receiving in that structure, is receiving the pair of electrons, this is carbon dioxide, that will make carbon dioxide a Lewis, this capital L, Lewis base. So that's one good example of Lewis acid and base reaction. In this particular synthesis, after rearrangement, it forms this stable species. So I give you more examples here so you can practice to identify the Lewis acids and Lewis bases. So you can practice with this. All right, here we finish chapter 16, general concepts of acids and bases. However, we are not done with acids and bases. We are going to cover more topics on acids and bases on the next chapter, chapter 17, application of what we just learned. Especially we are going to work with weak acids and bases. So we'll do on the next chapter. Buffer solutions, titrations, the equilibria of insoluble salts to find also the solubility product, KSP constant of insoluble salts. All right, so see you on the next video.